We also have something called a combination, which is a selection of items from a collection where the order does not matter. So the only three-person combination of Bill, Bob, and Mary is Bill, Bob, and Mary. Or in other words, the way that a combination differs from a permutation is that combinations are more about the group that you've created, like the group of people. It doesn't matter who's standing by who, it's still the same group of people. While a permutation depends on the order of the grouping. So if Bill and Mary switch spots, it's now a different ordering. In a combination, the order doesn't matter. So as long as it's the same objects within the group, it's the same combination. So any group in a different order would be the same combination of people. So even though we had 6 permutations when we had 3 people, if we want a 3-person group and we only have 3 people to choose from, we're only going to have one combination because it doesn't matter who's standing by who, it's still the same 3 people working together. And we can also talk about a combination of n elements taken r at a time. This time, rather than p, we're going to use c. Sometimes I say n pick r or n choose r. So the p one would be pick r, which is our permutation, and the c one would be choose r, which is our combination. And there's actually another notation for this, which would be like n p r or n c r. So if you see this, this is the same as the notation that we were writing earlier. You might see these like on your calculator. If CNR denotes the number of combinations of n elements taken r at a time, again with r less than or equal to n, then C, this should be a capital, NR is equal to P of NR divided by r factorial, or different notation here, which I think makes a little more sense, or looks a little nicer, is n factorial divided by n minus r factorial times r factorial. And notice this is actually the exact same thing. This part here is just this guy, and then we have that r factorial left in the denominator. Another equivalent notation for our combinations is what we have here. So this parenthesis with the n over r. This will not mean permutation. This is only for combination. So exercise 7. Let's calculate the following, starting with part A. So we have C of 8 and R. So how many combinations do we have of 8 elements taken 6 at a time? Well, jumping to this part of our formula, our n here is 8. So this is 8 factorial divided by 8 minus 6 factorial times 6 factorial, or 8 factorial divided by 2 factorial times 6 factorial. And let me just issue a word of warning. You do not want to simplify your numbers that are currently written in factorial notation unless they match exactly. So notice 8 factorial over 6 factorial is not the same as dividing by 2, right, and getting 4 and 3. So it's not the same as 4 factorial over 3 factorial. You can't simplify your numbers like you would if they were just normal numbers, because these aren't normal numbers, right? I mean, let me rephrase that. They are normal numbers, but they're not the number that they look like. They're kind of like disguised numbers, right? So in your calculator, if you did 8 factorial divided by 6 factorial, you would get 56. So on the left here, you would have 56. But if you did 4 factorial divided by 3 factorial, you get 4. So clearly, these are not the same fractions. So you cannot simplify the number in factorial notation because 8 factorial is not really 8. 8 factorial is 40,320. And 6 factorial is not 6, it's 720. Similarly, how 4 factorial is not 4, but rather it's 24. And 3 factorial is not 3, but rather it's 6. So even though it looks like you might be able to simplify them here, you really can't, because it's really these bigger numbers disguised in this notation. Maybe you could say it that way. So try not to fall into that trap of accidentally just simplifying like you used to. Remember that these are actually different numbers in a different notation. It's kind of like when we have numbers under a square root, and you can't simplify a number under a square root with a number that's not under the square root, right? Because really, it's not actually the number you see. It's like the number has a hat on, and the hat is a disguise, and it's actually a different number. Okay, so back to our problem. We can still simplify out the numerator until it matches one of the ones in our denominator. So I'll do 8 times 7 times 6 factorial. And at least now, since everything's being multiplied, I can simplify the 6 factorials because they match exactly, so they are the same. And then all I'm left with to calculate is 8 times 7 divided by 2 times 1, which gives me 56 divided by 2, or 28. Take a second and try part B on your own. Remember, this is the same notation, so n is our 40 and 2 is our r. Pause the video and then come back and check your work. And you should get back 780 different combinations of 40 elements taken 2 at a time. Exercise 8. A college student has 6 courses left in her major and plans to take 3 of them this semester. Assuming the student has the prereqs for all of the courses, determine how many ways she can select the 3 courses. Try this one again on your own. Pause the video and then come back and check your work. And actually take the time to pause the video and just try. So try to apply what we just learned, and then we can check our work together. Okay, if the student has 6 courses to choose from and she wants to take 3 of them, the order doesn't matter. For example, if you take art history and math and dance out of the 6 you had to pick from, it's the same as if you took math and then art history and then dance, right? It doesn't really matter which one you take first during the day or during the week. It just matters that you took those 3 particular classes during the semester. So this is a combination problem, not a permutation problem. So since it's a combination, we're doing a combination of 6 classes taken 3 at a time. Plugging this in, we end up with 6 factorial over 3 factorial, 3 factorial. That's 6 times 5 times 4 times 3 factorial over, I'm going to write one of them out because I know I'm going to cancel this other one. And if you multiply what's left, you're left with 20 ways. Exercise 9, we want to determine if the following describe a combination or permutation. So just like I went over in the last problem by writing down the different classes, I was just doing that to help myself figure out if I'm doing a combination problem or permutation problem. Or in other words, does the order in which I choose my elements matter? So it's important that you can be able to tell, because sometimes you're going to need to utilize your permutations and other times you're going to need to utilize your combinations, and it won't be laid out directly for you. So let's look at A through D and decide whether or not we think it's a combination or a permutation. Part A. 10 fans at a concert are chosen to come backstage after the show. Take a second and think about it and write down if you think this is a combination or a permutation. Again, we have 10 fans at a concert are chosen to come backstage after the show. If they pick 10 people to go backstage, if person 8 and person 9 switch seats, is it still the same 10 people that are going backstage? Yeah, so the order doesn't really matter here, so this would be a combination. Part B. A state elects a governor and a lieutenant governor from a pool of 8 candidates. Take a second and write down your guess. Okay, so they have 8 people to pick from, and let's say that the first person they pick will be the governor, and the second person they pick will be the lieutenant governor. So since there are specific positions for which that person could fill, the order does matter. Because if the first person is the governor and the second person is the lieutenant governor, then it matters who I choose first and who I choose second. Let's say Mark is the governor and Mary is the lieutenant governor. Then I could also have that Mary is the governor and Mark is the lieutenant governor. Or in other words, order matters, and this is a permutation. So that's a good thing to look for. If there's a specific role that's being filled, it's usually a permutation. Part C. Of the 6 optional community service projects in a service learning course, Haley picks 3 of them. Take a second to guess. This is similar to the problem we just did with picking the courses. It doesn't matter which 3 she picks, it's the same 3 regardless of which one she does first, so this is a combination problem. And lastly, part D. Mark looks over the novels on his bookshelf and lists his 5 favorites ranked 1 through 5. Take a second to guess. Since he's ranking his books 1 through 5, the same 5 books can be ranked in a bunch of different orders. So the order matters, and this is a permutation. Exercise 10. To play a lottery game, a person picks 5 numbers from 1 to 39 and then selects one more number from 1 to 19. Count the ways to play the game. Pause the video and try this problem on your own. It's a little bit more confusing than the ones we've done so far, but you have all of the tools to figure this out. So give yourself a minute or two to be confused and try a few different ways to see if you can figure out the number of ways that you can play this game. Then come back and we'll try the problem together. Okay, so this one is a little bit trickier than the ones we've done so far. So let's just start reading it again. To play a lottery game, a person picks 5 numbers from 1 to 39. Let's stop there and just figure out this little section. When it says they pick 5 numbers out of this larger amount of numbers, that makes me think either a permutation or combination of n elements taken r at a time. So now we just need to figure out, is this a permutation or is this a combination? Well, when you play the lottery, if you pick the numbers 5, 7, and 3, it's the same as if you picked 7, 5, and 3, or 3, 7, and 5. No matter what, you've picked the same 3 numbers. So the order does not matter when picking numbers in a lottery. It just depends on what numbers you picked. So this tells me that this is a combination. And it's a combination of 39 numbers, counting from 1 to 39. So 1, 2, 3, 4, 5, all the way up to 39. And I'm picking 5 of them. So out of my 39 elements, I want to choose 5. Then it says, then the person selects one more number from 1 to 19. If I'm only picking one number, I kind of can just go back to my fundamental counting principle, and I just need to figure out the number of ways that this event can happen. Well, the event is picking one number from 1 to 19, and there's 19 different numbers from 1 to 19. So I have 19 ways of doing this. Then applying the fundamental counting principle further, my first event is the one where I pick those 5 numbers. So my first event is C39.5. My second event is where I pick one more number, which we said had 19 options. And using my fundamental counting principle, I just need to multiply the number of options for event 1 times the number of options for event 2. Figuring out this first part, then I'm going to multiply by 19. If you simplify this, you get 39 times 38 times 37 times 36 times 35. This is going to be 34 factorial, so I'm going to simplify that, and then I just have that 5 factorial times that 19. Plugging this into your calculator, you get back 10,939,383 ways to play this game. Again, remember I kind of skipped a step here where I found that this was 34 factorial, so there would have been like a 34 factorial, 34 factorial, and then we got rid of those. And lastly, exercise 11. How many committees of 3 people can be selected from 5 women and 4 men if a committee must include at least 1 woman? Okay, when you're making a committee of 3 people, does it matter who's sitting by who? I don't think so. So if the order doesn't matter, then this is a combination problem. So I'm trying to find combinations of 3 people selected from this pool that has 5 women and 4 men, but I have a condition where the committee has to include at least 1 woman. Well, for starters, we can figure out how many different ways could you just make a committee of 3 people given these 9 people to pick from, right? So we have 5 women, 4 men, or in total, there are 9 people. So how many ways could I make a committee or a combination out of my 9 people if I only want 3 of them? So that's 9 factorial over 9 minus 3 factorial times 3 factorial. It's 9 factorial over 6 factorial times 3 factorial. So there are 84 different committees made up of 3 people out of the 9. However, that does not take into account the fact that we want the committee to contain at least 1 woman. So what we can do is we can figure out all of the committees that have no women and just subtract that from the total, and that should leave committees that have at least 1 woman, right? Because the only way that you're not going to have at least 1 woman is if you have a committee that's all men, right? Otherwise, you would have maybe 2 men and 1 woman, or 1 man and 2 women, or all women. So we just need to figure out how many of these there are and subtract that from the total. Or in other words, out of the 4 men, what happens if I choose all 3 of them? Right? So if I'm only looking at the men and I make committees of 3 of them, how many of those would there be? Which is just 4. So there's only 4 committees that would be of 3 people that were all men. So out of the total 84 committees, only 4 of them don't satisfy this requirement, which means that there are 80 different committees that make sure to have at least 1 woman.